Hello friends, I am Prof.Darshan Thakur from Terna Engineering College, Dharashiv. Welcomes you on my YouTube channel for this subject here, Control System Engineering. So friends, as far as our today's session is concerned, so one more time we will try to plot the dynamic characteristics of this control system. The way in which we are plotting the dynamic characteristics of that control system, that technique is nothing but what? The root locus curve, right? So let us quickly go through. The objective for our today's session is nothing but what? As you can see, such type of unity gain feedback system we are having with us, means whose feedback gain is exactly equals to 1 and whose open loop transfer function is given with this statement k into s plus 9 divided by s times of s square plus 4s plus 11, right? So in order to plot this root locus curve, there are 7 to 8 steps which we need to follow carefully. Then and then only we can plot the dynamic characteristics of this control system. So let us quickly go through the design step number 1 here. So within this design step number 1, we need to determine number of loci. So number of loci equals to maximum number of either pole or 0. So we need to determine how many number of poles and how many number of zeros we are having with us, right? So how to get the number of poles and number of zero? These are the desired frequencies. How we are getting these desired frequencies? By equating its numerator as well as denominator term equals to 0. If this numerator polynomial is being equated to 0, here numerator, within that numerator we used to have s plus 9, so s equals to minus 9. So that can be called it as a 0 of that open loop transfer function. So first desired frequency belongs to 0, which is present within this minus of 9, right? Then as far as this denominator term is concerned, so within this denominator polynomial, we used to have this s into this quadratic equation. So obviously when this s is being equated to 0, so s equals to 0, this will be the first pole, right? Then after that, this type of quadratic equation we are having with us, that is nothing but what? S square plus 4s plus 11. So with the help of this scientific calculator also we can determine the pole, but the algebraic method will be what? Minus b plus minus b square minus 4ac upon 2a. So here b is nothing but what? 4 minus 4 plus minus b square means 16 minus 4. A is nothing but 1, c is equals to 1. So minus 4 into 11. So 11 4s are 44 divided by 2 into a equals to 1. Right, so this whole term will become what here? So 16 minus 44, which exactly equals to minus 28. So minus 4 plus minus square root of minus 28 upon 2. This term can be rearranged. 28 means what? 4 sevens are 28. We can write in this manner. So minus 4 plus minus square root of minus into 4 into 7 equals to 28 divided by 2. So this whole term can be rewritten as a minus 4 plus minus the square root of 4 is exactly equals to 2. So plus minus 2 into minus root 7 divided by 2, right? So the roots are nothing but what? Minus 4 divided by 2. So minus 2 plus square root of 7 equals to what? As we are having the negative term within that square root sign, so it will become plus minus j square root of 7 6 means it is 2.64, right? So the poles are nothing but what? This will be s1, s2 is present at minus 2 plus j 2.64 and s3 will be present at minus 2 minus j 2.64. So in this way, first of all we need to determine how many poles and how many zeros we are having with us, right? Because number of loci equals to what? Maximum number of either pole or zero. So we are having 3 poles. Out of that 3 pole, 1 pole is being located at origin and remaining 2 poles are nothing but what? Imaginary poles, which are exactly equals to minus 2 plus minus j into 2.64, right? So we are having 3 poles and 1 0. So number of loci equals to 3 because maximum number of pole is how much here? 3. Then after that, within that second step, we need to determine or we need to plot the pole 0 plot here basically. Okay friends, so within that step number 2, as I told you earlier, we need to draw the rough pole zero plot. So this S domain representation, which consists of this real and imaginary part, which ranges from minus infinity to plus infinity, plus j omega to minus j omega. So the first pole is located at origin. Remaining two poles are nothing but what? Minus 2 plus j 2.64. So this will be plus j. I will rub this step number 1 for sake of this moment in order to so this will be 1j, 2j, 3j, minus j, minus 2j, minus 3j. This will be minus 1, minus 2, and see, one pole is present at minus 9. So this will be, or instead of that, see, we will continue this axis, minus 2, minus 3, minus 4, minus 5, minus 6. So 1 0 is at minus 9, and remaining two poles are nothing but what? Minus 2 plus 2.64. So somewhere in between plus 2j and minus 3j we will have this 2.64j, right? Similarly, within this third quadrant also, this is minus 2, minus 3. So the pole is present at minus 2, minus 2.64j. So the position of this pole will be minus 2, minus 2.64j plus 2, minus 2 plus 2.64j. Right. So this will be your step number 2. Then within that step number 3, we need to determine number of asymptotes and their angle. So number of asymptotes equals to p minus of z, right? So here p equals to 3 and z equals to 1. So there are two asymptotes, and these two angles are nothing but what? A1 and A2. How to get this A1? So we used to have this relation 2x plus 1 divided by 3 into 180 degree. 2x plus 1 divided by 3 into 180 degree. So within that first iteration x equals to 0. Within that second iteration x equals to 1. So when x equals to 0, 3 6 18. So 60 degree. When x equals to 1, 3 will get cancelled. So 180 degree. So asymptote angle number 1 is 60 degree. Asymptote angle number 2 is nothing but what? 180 degree. Then after that, in that step number 4, what we need to do? In that step number 4, we need to determine these fellow qualities as a centroid or sigma c, the intersection on that real axis. So for that purpose, what we need to do? We need to follow this formula: summation of real part of pole minus summation of real part of 0 divided by p minus of z, right? So as we are having 3 poles, out of that 3, one is located at origin, remaining 2 are the imaginary poles. Their real parts are nothing but what? Minus 2 and minus 2. Again we are having 1 0 which is located at this minus 9. So it will become minus 4 plus 9 divided by p minus of z. P equals to 3, 2. So it will become 5 by 2. So it will be 2.3 or 2.4, right? So in this way, this centroid or sigma c is being located. Then after that, step number 5 will be what? Usually step number 5 is nothing but the calculation of breakaway point, right? So breakaway point is nothing but what? The intersection on that real axis. But as we are having the real as well as imaginary point, so we are not having the valid breakaway point. So this step is being skipped, right? Then after that, in that next step, we need to determine the angle of departure and the intersection on that imaginary axis. So whenever we are having the imaginary pole at that time we need to determine the angle of departure. So we need to understand what this angle of departure stands for, right? So in order to determine this angle of departure, as I told you earlier, first pole is present at origin, right? Second pole is present at -2 plus 2.64 J, and third pole is present at -2 minus 2.64 J. So first of all, we need to interconnect all these poles and zeros with each other like this. So the angle made by this pole, which is present at -2 plus 2.64 J with respect to this pole which is located at origin, that can be called it is as a phi 1, right? Similarly, the second pole is present at -2 minus 2.64 J. So the angle made by this pole with respect to this pole which is located at that origin, or with respect to that real axis, that is nothing but what? Phi 2, right? So here we can say that clearly phi 2 is exactly equals to 90 degree. Now what about this phi 1? How to get this phi 1, right? So in order to measure this phi 1 with the help of that protector, we need to measure this phi 1, means we need to put this protector like this and we need to measure this angle. So after going through this measurement, phi 1 equals to, I think it is 121 degree. Then after that we are having one 0 which is placed at minus of 9, right? So what we need to do, first of all we need to interconnect this 0 with this pole which is located at -2 plus 2.64 J, and the angle made by this 0 with respect to this pole, that can be called it is as a phi 3, right? So what we need to do, how to get this phi 3 fellow? So with the help of this protector, so you need to put this protector like this and you need to measure. So as a result of measurement, phi 3 equals to 21 degree, or by using this trigonometric method also we can determine the angle phi 3, right? So as far as this phi 3 is concerned, so phi 3 is nothing but what? The angle made by this 0 with respect to this pole. So as far as this phi 3 is concerned, in order to determine this phi 3 with this tan method, tan theta equals to what? Its opposite side. So opposite side is nothing but what? This height, which exactly equals to how much here? Plus 2 point, which is somewhere written on that board, plus 2.64. So tan theta equals to its opposite side 2.64 upon its adjacent side. Adjacent side is nothing but what? This real axis, which starts from this -2 and ends at this -9. So it is -2 minus 9. So obviously -2 minus 9. So minus minus again, it will become minus of 7, right? So theta equal to tan inverse of 2.64 upon 7. This will give you 20 or 21 degrees. So in this way, what we need to do, we need to determine the angle of departure within that step number 5. So angle of departure equals to 180 degree minus summation of angles made by poles plus summation of angle made by 0, right? So once this angle of departure is being tabulated, then after that we need to determine the intersection on imaginary axis, right? So let us quickly go through this step number 6. So before proceeding for next step, one small correction which we need to do here. The number of asymptotes and angle of asymptotes what was already it is being tabulated. So in that step, number of asymptotes equals to p minus of z 2, 3 minus 1 it is 2. So what we need to do, within this denominator here, angle of asymptotes equals to 2x plus 1 into 180 degree divided by number of poles minus 0. So here number of poles equals to 3, number of zeros equals to 1. So it will become 2x plus 1 upon 2 into 180 degree, where x equals to 0, right? So 2 nines are 18. So instead of 90 degree it will become, instead of 60 degree it will become 90 degree, that we need to know. Within that second angle of asymptotes, 2x plus 1 into 180 degree divided by 2. So x equals to 1. Again, so here 2 plus 1 it is 3 into 180 degree divided by 2. So again it is 2 nines are 18. So 9 into 2, sorry 9 into 3, 9 3s are 27. So 270 17 degree. That will be angle of asymptote number 2. Then after that, theta 1 is concerned. So as I told you earlier, here theta 1 is exactly equals to what? With the help of this protector, when we will try to measure this angle made by this pole with respect to this real axis, so actually it is 127 degree. So angle of departure for this pole, which was located at -2 plus 2j plus 2.64j equals to what? So in order to determine this angle of departure, 180 degree minus summation of angles belongs to poles. So we are having 3 poles, out of that one is located at origin and we are having 1 0, right? So phi 1 equals to 127 degree, right? Phi 2 equals to 90 degree and phi 3 is nothing but what? The angle made by this 0 with respect to this pole, right? Which exactly equals to how much it is? It is 21 degree. So angle of departure for this pole equals to 180 minus 127 plus 90 plus 21, right? So angle of departure equals to minus 17 degree, right? For which pole? Which was located at quadrant number 2, whose location is nothing but what? -2 plus 2.64j. Similarly, another pole which was located at -2 minus 2.64j. So these two are the symmetrical pole. So if angle of departure for this pole is minus 17 degree, so for this pole obviously it will become plus 17 degree. So how to take this plus and minus 70 degree angle of departure? So for that purpose you need to put this protector like this over this pole which was located at -2 plus 2.64j, and we need to measure the angle is nothing but what? Minus 17 degree. So from here 0, 10, 20. So here somewhere we will have this 17 degree, right? And similarly for this pole we need to put this protector like this, right? And the angle of departure is how much? It is plus 17 degrees. So like this, somewhere we are having this plus 17 and minus 17. Then after that we need to determine the angle of the intersection of this root locus on this j omega axis. The intersection of this root locus on that imaginary axis, right? So in that next step, what we need to do here? Okay friends, so in that next step we need to find out the intersection of this root locus on this j omega axis or onto this imaginary axis. So for that purpose, this relation we need to use d plus kn equals to 0, where d is nothing but denominator polynomial, n is nothing but the numerator polynomial. So this denominator polynomial is nothing but this whole term, s into s square plus 4s plus 11. So as it is we need to write plus k into the numerator polynomial is nothing but what? S plus 9. So after going through this mathematical simplification, when this s will get multiplied with this parenthesis, so it will become s raised to 3 plus 4s square plus 11s plus ks plus 9k equals to 0, right? So with the help of this root stability criteria, we need to declare, or we are supposed to declare the elements of this root array. So in order to declare the elements of this root array here, we need to write this characteristics equation in descending order. So s raised to 3 plus 4s square, as we are having two terms belongs to s, so s these two terms can be considered as a common term. So as a result of this, whole term will become 11 plus k times of s plus 9k. So this first term can be mapped as a0, a1, a2 and a3. So after that we need to declare this type of root array where highest degree of s is nothing but what? 3. So 3, 2, 1 and 0. As far as the first row is concerned, so we need to collect all the elements which are lying at even position, means a0 and a2. Within that second row we need to consider all the elements which are lying at odd position, means a1 and a3. So the elements are nothing but what? 1 into 11 plus k, 4 and 9k. As far as the third element is concerned, or the element which belongs to this s raised to 1 row, previous two rows are being taken into account. Along with this cross multiplication, it will become what? 4 into 11 times 4 into 11 plus k minus 9k upon 4. So it will become what? 11 4s are 44 plus 4k minus 9k divided by 4. So it will become what? 44 minus 5k divided by 4, right? Here the element will become 0, right? Similarly, the last element which is to be tabulated from first two rows. So first two rows are nothing but what? 4 9k, 44 minus 5k upon 4 and 0, right? So this whole term will get multiplied with this 9k divided by this whole term. So these two terms will get cancelled. Remaining term is nothing but what? 9k. So from this root array, we too can determine the marginal value of that k, right? So the marginal value of that k is to be tabulated from this row. 44 minus 5k upon 4, it should be greater than 0 obviously. So k equals to what? The 44 upon 5, so which exactly equals to 8.8. We are supposed to determine the intersection of this root locus on this imaginary axis. So with the help of this auxiliary equation, we need to tabulate the intersection point of this j omega axis. So how to get the auxiliary equation? The auxiliary equation is to be determined from that particular row, or which row is to be identified as a auxiliary equation row. The answer for that question is nothing but what? The marginal value of that k is being tabulated from row number 3. So its previous row can be considered as a auxiliary equation row, right? So auxiliary equation will become what here? 4s square plus 9k, here s raised to 2. The previous even element is nothing but what? S raised to 0. So your auxiliary equation will become 4s square plus 9k equals to 0. As we know, marginal value of this k is exactly equals to how much? It is 8.8. So from this marginal value, here 4s square equals to minus 9 times of k. So obviously s square equals to what? Here 9 minus 79.2 upon 4, where k is nothing but what? 8.8. So 8.8 into 9. So minus 79.2 upon 4. So which exactly equals to minus 19.8. Right. So basically s equals to what? When this whole term is being considered within that square root value. So obviously when we are having the negative term within this square root operator, so we are having such type of imaginary term. So the intersection points will become what? Plus minus j 4.4, right? So this root locus will try to intersect this imaginary axis on plus and minus j 4.4. Now we will plot the root locus curve for this given open loop transfer function with this all tabulated values. Okay friends, so lastly we will plot this root locus curve. So in order to plot this root locus curve, these are the few parameters which already we had tabulated from design step number 1 to design step number 7. These parameters are nothing but what? Like angle of asymptotes. Angle of asymptotes for first asymptote will be 90 degree. Angle of asymptote for asymptote number 2 will be at 270 degree. The angle of departure for this pole which is present at minus 2 plus 2j is exactly equals to minus 17 degree, and the pole which is present at minus 2j is exactly equals to plus 17 degree. Here the centroid is exactly equals to 2.5 plus 2.5, and the intersection point on this j omega axis is nothing but what? Plus and minus 4.4j, right? So first of all, what we need to do? First of all, we need to draw these two asymptotes. So these asymptotes are to be drawn from this centroid. So this centroid is located at 2.5. This is 2 and 3. So in between these 2 and 3, see, this will be the first asymptote, this straight line, whose angle is exactly equals to how much here? 90 degree, and this will be what? The asymptote number 2, right? So this angle will be what? 217 degree. This will be asymptote number 2. Then after that, as we know, that can be called it is as a theta 1, the angle made by this pole which was located at minus 2 plus 2j with respect to this real axis, right? Theta 2 is nothing but what? The angle made by this pole located at minus 2j with respect to this real axis, 90 degree. Phi 3 is nothing but what? The angle made by this 0 which was located at minus of 9 with respect to this pole. So here the angle of departure for this pole is exactly, already it is being tabulated in design step number 5 or 6, which exactly equals to minus 17 degree. So how to get this minus 17 degree? Here we need to put this protector like this. So somewhere here we will have this minus 17 degree, and it will try to this is nothing but what, 45, what we can say. So minus 17, somewhere like this, right? And it will try to intersect, this will be minus 17 degree, and for this pole which is present at minus 2j, the angle of departure will be plus 17 degree. So we need to put this protector like this. So somewhere here we will have, so this angle is nothing but what, plus 17 degree. So this root locus will intersect this j omega axis on plus 4.4j and minus 4.4j. So this root locus 4.4j, and again it will become parallel to this asymptote. Similarly, the second arc of this root locus start from minus 2j with angle of departure 17 degree like this, and it will try to intersect this imaginary axis on minus 4.4j, and again it will parallel to this asymptote whose angle is nothing but what, 217 degrees. So this is how your root locus will look like for this open loop transfer function, whose gain is exactly equals to k into s plus 9 divided by s into s square plus 4s plus 11, which consists of 1 0 and 3 poles. Out of that 3 pole, 1 is real and remaining 2 are nothing but what, the imaginary pole. So I just hope you had understand all these things belongs to this root locus curve. Thank you.